It's a very human trap to fall into.
Oh, definitely.
Like, have you ever been working on a project? Maybe you're organizing your garage or, I don't know, drafting an important email, and you decide to make it just a little bit more complicated.
Right, because you think it's going to be more efficient or something.
Exactly. Instead of just, putting the hammer in a toolbox, you build this complex, color-coded, cross-referenced pegboard system.
And then it ends up taking you 10 times longer to actually maintain it.
Yes. We sacrifice the simple and readable because we're just utterly convinced that, complex means optimized.
Classic mistake.
It really is. So today, our mission on this deep dive is to find out if sacrificing readability for supposed optimization is actually worth the effort.
I love this topic.
Right. And we have the perfect source material to test this out. It's this incredible breakdown by a developer named Ang titled Notes-on-Haskell-Programming, Part 202. Why memory safety doesn't mean better performance.
It's a brilliant case study, really, because Ang essentially puts this exact human tendency under a microscope, using software engineering as the testing ground.
Which is the perfect place for it.
Yeah, totally. In the programming world, especially in a functional language like Haskell, there's this constant tension. You have this struggle between writing elegant, readable code and writing highly optimized, hardware-hugging code. It's a daily battle.
Okay, let's unpack this. Because to really understand Ang's experiment, we need to look at the specific code that kind of sparked the whole debate.
Right, the inciting incident.
Yeah. So Ang originally wrote this really clean line of code using a list comprehension. The goal was super simple. Look through a massive list of data blocks, find all the volume headers, and just count them.
Using a length function and some basic unit values.
Exactly.
And conceptually, it was elegant. I mean, anyone glancing at it could intuitively grasp its purpose.
It's very readable.
Very readable. It was just mapping over a list and tallying up specific items. But, as often happens in software engineering, a code review introduced some doubt.
Oh, the dreaded code review.
Right. Someone raised a concern that this elegant code might actually cause a memory leak.
And, in the context of Haskell, a memory leak is a very specific flavor of nightmare, right? We aren't just talking about a program forgetting to empty the trash.
No, far from it. It comes down to how Haskell evaluates code by default. It uses something called lazy evaluation.
Lazy evaluation.
Okay,
Right.
so when you tell Haskell to filter a list or count items, it doesn't necessarily do the computation right away.
Wait, really? It just ignores you?
Kind of. Instead, it creates what's called a thunk.
A funk. What an incredible word.
It is. Basically, it's a mathematical IOU in the system's memory. It essentially says, I promise to calculate this specific value the moment you actually need it.
Okay, so if you're processing a list of, say, 100,000 data blocks, you might be generating 100,000 of these IOUs in memory before the program ever gets around to actually counting them.
Exactly. So the memory leak isn't lost data.
It's the sheer weight of all those uncached promises choking the system.
That is the exact fear. And because of that fear, someone suggested Ang throw out the simple list comprehension.
Throw out the good code.
Right. And rewrite the logic using an explicit strict fold function.
Okay, fold. Spelled with an L at the end, right?
Yes, fold. And actually, there's an apostrophe at the end of fold, which is the crucial part. It denotes strictness.
So no more IOUs.
Exactly.
Yeah.
It forces the program to evaluate the data right then and there. It tears up the IOUs as it goes and just maintains a running tally without building any intermediate lists in memory.
Okay, I want to introduce an analogy for you as you're listening, just to help visualize these two approaches.
Oh, I love your analogies. Go for it.
So think of Ang's original code like a beautifully simple baking recipe. Mix flour, add water, bake.
Simple, clean.
Right. It's readable. It gets the job done. But this suggested fold rewrite. It's like throwing away that simple recipe and replacing it with a dense industrial operations manual.
Oh, man.
Like engage mechanical agitator at 45 degrees, monitor moisture retention metrics, apply thermal radiation.
Yeah, that sounds exhausting to read.
It is. The industrial manual guarantees you won't overflow the mixing bowl, which prevents the memory leak, but it is a total nightmare to read.
It really is.
Which leads to my immediate question. If I'm forcing my brain to translate an industrial manual just to bake a cake, that cake better materialize instantaneously, right?
That is the logical leap we all make.
Right.
We assume the cognitive pain of writing and maintaining complex code buys us this massive reward in performance.
It has to. Otherwise, why do it?
Right. But rather than just arguing about theory, Ang decided to run a highly controlled experiment to see if the industrial manual actually outperformed this simple recipe.
A bake-off.
A bake-off.
Mm-hmm.
They used a benchmarking library in Haskell called Criterion to get, really precise timing.
And to make the test fair, they needed a substantial data set. So Ang generated a mock list of 100,000 data blocks.
It's a good sample size.
Yeah, and it simply cycled over and over through 3 types of data: a volume header, a paragraph of text, and a chapter header.
Right. And they tested 3 distinct approaches against this data set.
Okay, let's hear the contestant.
Contestant number 1 is the original method.
The simple baking recipe.
Exactly. It uses length with a list comprehension, dropping a placeholder token, a unit value every time it sees a volume header, and then it just counts those tokens.
Beautiful. And contestant number 2 is our heavyweight, the optimized method.
The industrial manual.
Right, the explicit, strict fold rewrite designed to prevent that thunk buildup. It manually tracks the state of the tally, stepping through the list item by item.
And to round out the experiment, contestant number 3 is the middle ground.
Okay, the middle ground.
It's another list comprehension, but instead of using length and unit values, it uses the sum function.
Oh.
So it essentially says, every time you see a volume header, yield the integer 1, and then just add all those ones together.
Okay, so the board is set. We've got the beautiful original, the ugly but theoretically fast rewrite, and a slight variation of the original. We have to look at the execution now.
Yeah, the actual race.
Ang first ran these tests using GHC's interpreter via the stack runcat command.
Right, the interpreter.
And the defining feature of the interpreter is that it gives you fast, non-optimized compilation. It's built for rapid prototyping.
Yeah, it reads the code and executes it quite literally without trying to analyze or improve the underlying logic.
Okay, so give us the results. I'm fully expecting the ugly fold code to just crush the simul recipe here.
Well, what's fascinating here is how the literal nature of the interpreter completely flips our expectations.
Wait, really?
Yeah. When forced to run exactly what was written, the dense, explicit fold approach, the industrial manual, was actually the slowest.
Are you kidding? The manual rewrite was the slowest?
The slowest. It averaged around 12.96 milliseconds to process the 100,000 blocks.
Wow.
The original readable list comprehension was the fastest at 8.842 milliseconds.
That's a huge difference.
It is. And it was closely followed by the middle ground sum method at 9.264 milliseconds.
Wait, so trying to outsmart the system by writing hyper-specific manual code actually made it worse?
The degraded performance, yeah.
Why? Why does explicitly telling the computer how to manage its memory slow it down in this environment?
Well, it comes down to the overhead of parsing and evaluating complex syntax on the fly.
Ah.
An interpreter doesn't compile the code down to highly efficient machine instructions beforehand. It has to constantly traverse the abstract syntax tree, the structural representation of your code while it runs.
So it's constantly having to reread the manual.
Exactly. The original code used built-in, highly refined primitive functions for its counting logic. By rewriting it manually with fold, and didn't streamline the machine's execution, they just introduced structural overhead.
That makes so much sense.
The interpreter had to spend more time reading and evaluating those cryptic, wordy instructions step by step.
So you added cognitive load to the machine without providing any structural benefit.
Precisely.
If the interpreter is a chef, we essentially stop them from using their intuition and force them to read every single word of the industrial manual before taking a step.
And that takes time.
It totally takes time. But of course, prototyping isn't production. No one ships an interpreter to their end users.
No, definitely not.
So here's where it gets really interesting. What happens when we unleash the full power of the machine and actually compile this code for production?
This is where Ang brings in the heavy machinery. They reran the benchmark, but this time they compiled the code passing the Anisto flag to the GHC compiler.
Okay, the Agile2 flag. That's essentially the gold standard for turning on the compiler's most aggressive optimization suite, right?
Oh, yeah. It stops reading the code literally and starts actively restructuring it to run as close to the bare metal as possible.
I love that phrase, bare metal.
It's a good one. And it unleashes an incredible arsenal of tools behind the scenes to do it. For instance, it performs worker wrapper transformations.
Worker wrapper.
Yeah, it's this brilliant mechanism where the compiler takes a function and splits it in two. The wrapper handles the standard Haskell data types and the lazy evaluation logic we talked about earlier.
Okay.
But it immediately passes the actual raw data to the worker, which is a specialized version of the function that just crunches unboxed primitives in a tight loop.
Okay, if we think about that mechanically, Unboxed primitives mean we are stripping away all the expensive packaging around the data.
Right.
Instead of keeping a pointer in memory that references an integer sitting somewhere else on the heap, the unboxed primitive strips away the pointer and just keeps the raw binary number directly in the CPU's register.
That structural shift is massive for performance.
I can imagine.
If the interpreter was a chef reading a recipe and walking back and forth to the pantry for every single ingredient, the Endo2 compiler is like a hyper-efficient restaurant consultant.
Oh, I like that.
It redesigns the entire layout of the kitchen, moves all the raw ingredients directly to the prep station, and eliminates every single wasted movement.
So it's like strapping the runners into high-speed bullet trains.
Exactly. But the real magic trick of the ASO2 flag, especially for this benchmark, is a mechanism called list-fusion.
Right, list-fusion.
The Haskell community vividly refers to this as deforestation.
Deforestation. Let's break down the mechanics of that because it's absolutely vital to understanding Aang's final results.
Yeah, so if our original list comprehension code is conceptually building a forest-like, a massive intermediate list of unit values in memory, just so it can count them, deforestation ensures we never plant those trees in the first place.
Wow. Instead of allocating memory for a massive array, filling it with data, and then traversing that array a second time to tally it up. Wait, sorry, so it just skips that entirely.
It's entirely.
So it turns the process into a bucket brigade, right?
That's a perfect mechanical analogy. The compiler sees that the intermediate list is just a temporary stepping stone. So it fuses the generated function and the counting function together.
That is so smart.
It produces an item, passes it directly down the bucket brigade to the counter, and discards it immediately. The massive intermediate list never materializes in memory.
With the restaurant consultant having completely overhauled our kitchen and implemented this bucket brigade, what do the final numbers look like?
We're moving from the realm of milliseconds down to microseconds.
Which is a massive leap in processing power. Did the ugly industrial fold code finally prove its worth under the pressure of the compiler?
Well, the final compiled numbers are staggering compared to the interpreter.
Hit me with them.
Contestant number 2, the explicit fold manual rewrite, crossed the finish line at 280.4 microseconds.
Okay.
Contestant number 3, the sum comprehension, came in at 280.8 microseconds. And contestant number 1, the original simple recipe, came in at 288.4 microseconds.
Okay, so technically speaking, 280.4 is the lowest number. The cryptic fold code did win the compiled race.
It produced the lowest integer on the benchmark yet.
I sense a but coming.
There is a huge but. Looking at raw numbers without the engineering context is a trap. If we connect this to the bigger picture, that win is an illusion.
Because we are talking about a delta of exactly 8 microseconds between the absolute fastest run and the absolute slowest run.
Exactly. Which is virtually meaningless.
Meaningless.
Totally. An 8 microsecond variance is entirely within the margin of standard system jitter.
Ah, system jitter.
Yeah. While your computer is running this incredibly fast benchmark, the operating system is doing thousands of other things in the background.
Right, checking for updates, syncing files.
It's managing network packets, dealing with CPU cache misses, maybe slightly thermal throttling because your room is warm.
The OS is essentially breathing, and that background breathing steals microscopic fractions of processing power.
Exactly. If Aang ran this benchmark 10 more times, the simple code might win half of them, purely based on random background noise. It's a statistical dead heat.
It is a dead heat. And the reason why they ran at identical speeds is, frankly, the most beautiful part of this entire deep dive.
It really is. Remember the deforestation concept? List fusion.
Right, the bucket brigade.
When the GHC compiler's NACO2 flag looked at all three of those distinct pieces of code, the simple recipe, the tweak sum recipe, and the dense industrial manual, it saw straight through the syntax.
It just ignored how they were written.
Basically, it analyzed the underlying mathematical intent of the programmer, and through stream-fushion, the compiler essentially flattened all three approaches into the exact same optimized bare metal loop.
That is mind-blowing. The compiler is so sophisticated that it realized, I see what you're trying to achieve. You wrote it 3 different ways, but the optimal way to execute this mechanically on a CPU is path X.
Yep.
And it just forced all 3 sets of code into the path X configuration.
It stripped away all the intermediate lists, it removed the fluff, and it just executed the underlying truth of the problem.
Wow.
Which proves Aang's ultimate suspicion. This aggressive compiler optimization handles the dreaded memory leak, regardless of how the code was originally written.
So the compiler fixes the thunk buildup for you.
It fixes it for you. Writing the manual fold rewrite to try and outsmart the system was entirely utterly unnecessary.
So what does this all mean for you, the listener?
That's the big question.
Whether you are writing functional code in Haskell, designing a database schema, or just setting up a project management board for your team, the takeaway here is profound.
Definitely.
The original code, the beautiful, simple, readable recipe, was completely adequate from the very beginning.
It was perfect.
It had excellent readability, it was concise, and when pushed to the absolute limit in production, the automated tools behind the scenes brought it up to maximum speed anyway.
But, it requires a paradigm shift for a lot of engineers.
How so?
You have to trust the ecosystem. Compilers like GHC have decades of peer-reviewed computer science baked into them.
Decades of it.
Unless you are in a domain where you are absolutely desperate to squeeze out a microscopic theoretical drop of performance like, say, high-frequency algorithmic trading, where a microsecond of latency has a quantifiable dollar value, you shouldn't be micromanaging the machine.
Right. You write for the human who has to read and maintain the code 6 months from now, and you let the tools do their job.
Exactly.
Eng's benchmark definitively proved that ugly, clever manual optimization didn't beat the compiler. When unoptimized, the manual approach was slower due to overhead. When optimized, the compiler leveled the playing field entirely.
It completely leveled it.
Proving that readability absolutely didn't have to be sacrificed for performance.
This actually raises an important question for you to consider in your own work, regardless of your specific field.
Oh, lay it on us.
As our automated tools, our compilers, our software engines, and increasingly, our AI systems become incredibly sophisticated at optimizing tasks behind the scenes, is our human obsession with micromanaging efficiency actually becoming a relic of the past?
Ooh, that's a good question.
Right. Are we wasting our time and energy trying to do the machine's job when we should be focusing entirely on making our ideas clear, readable, and fundamentally sound?
That is the perfect note to end on. The next time you catch yourself building that overly complex, color-coded pegboard in the garage, ask yourself if you're writing a simple recipe that someone else can easily follow, or if you're drafting an industrial manual for a result that's going to be exactly the same either way.
Keep it simple.
Exactly. Thank you so much for joining us on this deep dive. Keep asking questions, keep prioritizing clarity, and we will catch you next time.